Let's talk now about how to approach a titration problem. So we see we're starting with 100 milliliters of 0.5 molar HCl, and that's titrated, keyword there, with 0.2 molar sodium hydroxide. And it wants us to determine the following. The very first thing we're going to do is decide what type of titration do I have. There are 4 basic types: strong acid, strong base, strong acid, weak acid, strong base, and weak base, strong acid. The strong titrations are really similar and the weak titrations are really similar, but it's really helpful if right off the bat we know which type we're dealing with. So to figure this out, all we need to do are look at what we start with. So here I have 0.5 molar HCl, and I recognize that guy is a strong acid. And I have 0.2 molar NaOH. I recognize that that guy is a strong base. Therefore, I must have a strong acid, strong base titration. And I like to know that because then I have a general idea of what to expect and what I should be doing during my titration problem. So if I think about what my titration curve should look like, we've got pH on the y-axis, and we've got the amount of strong base added on the x-axis. My curve should look something like this. General shape, not a beautiful picture, but it doesn't have to be. And my equivalence point is going to be right at the center of that steep part of my titration curve. So it's good to have a general idea of what your titration curve looks like, because then you know what you will have and what you won't have. For instance, strong acid, strong base titrations don't have a buffer region, so I'm never going to have a buffer when doing this titration problem. I also like to think about what the pH is at my equivalence point. And for a strong acid, strong base, that pH is always 7. So now that I have a general idea of what I'm looking for, I can look back over at my problems and decide where I want to start. I don't have to start with the very first question, and I very rarely do actually. Looking back over my questions, we can see we've actually answered this question right here. The pH at the equivalence point for a strong acid, strong base titration, that's always 7. So you can see right away I've answered one just by thinking about what type of curve I have. Now let's think about the next place to start. I always like to start here. If we can figure out the volume required to reach the equivalence point, then for every other question we can think about where we should be on the titration curve so we know what answers we should expect. So I'm going to start there. Now obviously I'm going to need some more room. So I just put this part of the problem on a separate page. We can see it's the same thing, has the same beginning information, but I'm only concentrating on this piece right now, the volume of NaOH required to reach the equivalence point. First thing we need to do is write a chemical reaction between these. So I have 0.5 molar HCl and 0.2 molar NaOH, so I want to react the HCl with the NaOH. I like to make my life simple. And what I like to do is every time I have a strong acid, I recognize that I can actually call that H3O+. Because all strong acids do is immediately dissociate into H3O+. Similarly, if I have a strong base, I can go ahead and represent that as hydroxide, OH-. And if I write my reaction between those two, it's going to make my life a lot easier. So I have H3O plus OH-. Acids always donate, so I'm going to end up with H2O, and then in fact a second H2O, so 2 waters over here. And now I don't have to think about double displacement and where the sodium goes, where the chlorine goes. It's really easy. I just think that acids donate hydrogen, and I can easily predict my products. The next thing I like to do is organize my information. So what do I know about the acid? I'm going to put that right underneath him. I know that I started with 100 milliliters of acid, and I know that it's 0.5 molar. What do I know about the base? I don't know the volume of base. That's my question, and I do know that it's 0.2 molar. Okay, so that's what I know about the acid and base. I really don't care about the waters. I'm not worried about making products. I'm just worried about how much base I need to use up all my acid. So that's another key thing. When it says the volume of NaOH needed to reach the equivalence point, we need to keep in mind that at the equivalence point, the HCl and the NaOH are equal. What it's really asking is how much base do you need to add to exactly use up all of the acid that you started with. So at the equivalence point, the moles of H3O plus and the moles of OH minus are going to cancel each other out. So since they're going to be exactly equal there, I can just set up a nice little baby stoichiometry problem in order to figure out how much OH minus I need to add to get to that point. Basically, how much sodium hydroxide will cancel out my HCl. So right now I have a number, and then I have 0.5 m, but we need to keep in mind that 0.5 m really means 0.5 moles per liter. Big M stands for moles per liter. Same thing over here. 0.2 m, that really means 0.2 moles per liter. So I have a number, 100 milliliters, and then I have two ratios. Anytime I do a conversion problem, I'm going to start with the number just by itself. So I'm going to start with this 100 milliliters. And we can see the first thing I'm probably going to need to do is get rid of these milliliters and turn them into liters. So in every 1 liter, there's 1,000 milliliters. Then I'm just going to follow the same basic steps I do for any conversion problem. I have liters on top, so I need to put liters on the bottom over here. And I want to keep in mind that I'm talking about the H3O plus right now. So I've used up my 100 milliliters. Now I see, ooh, look, there's liters on the bottom here, so I can plug in this. I have 0.5 moles H3O plus in every 1 liter. So I've used that up. I don't have any more information about H3O plus, but I am in moles right now. And I know back from 1211 when we're doing stoichiometry, once I end up in moles, if I have a balanced chemical equation, I can go from moles of one thing to moles of another thing, which is exactly what I want to do. So I want to get rid of these moles of H3O plus, and I want to turn them into moles of my base, OH minus. So all I need to do is look back at my balanced chemical equation, and I see that it's a 1-to-1 ratio. Alright, now I'm in moles of OH minus. I must be pretty close. I know that since I have moles on top, the moles of OH minus are going to have to go on the bottom. I look at the information I have, and I say, oh look, there's a moles. So 0.2 moles corresponds to every 1 liter. And I say, haha, I asked for volume, that's exactly what I got, so now I can just plug this into my calculator, and I see that I get 0.250 liters of my strong base. Personally, because we were talking about milliliters, I like to convert this back to milliliters, so I just keep in mind there are 1,000 milliliters in a liter, so I see that I'm going to need 250 milliliters of the base to reach the equivalence point. So I just write my little equation, I organize my information, do a little baby stoichiometry problem, and I can figure out the volume needed to reach the equivalence point. So I'm just going to go back up and record that here so we can keep track. I also like to mark it on my graph, because now when I look at my other problems, I can think about, okay, am I before or after the equivalence point? And then I know what to expect. So for instance, in problem 1, the initial pH, I'm going to be right about there, so I should have a very acidic pH. Number 2 here, the pH after 50 milliliters of sodium hydroxide is added. Well, the equivalence point is at 250, so 50 might be, I don't know, somewhere right around there. And we can see that that should still be very acidic. My pH must be less than 7 because I haven't reached the equivalence point yet. On the other hand, the pH after 300 milliliters of sodium hydroxide, that's going to be after the equivalence point, maybe around there, and at that point I should have used up all of my acid, and then all I have left is base. So by figuring out where we are on the curve, we can really gauge our expectations. So let's go ahead, and now I'm just going to go in order. Now that I have my equivalence point, I know what to expect, I'm just going to start at the first one and then go from there. So here's a prettier version of this curve. I sketch a little one there, but I'm not a beautiful artist, so if you couldn't really read my handwriting there, we can see we have the same general idea. We have pH. We know my equivalence point occurs at 7 here. When we're ignoring that, that would be at our 250 milliliters. But this is just to give us the general idea of what these pH curves look like. You sketch one for yourself. Doesn't have to be beautiful, but it should at least be good enough that you can read the different regions and really know what to expect. Oops. So, again, I'm just giving each of these their own separate page, so I'll have room to work them, and they're all separate problems, so I don't need to look at more than one at a time. So I have my initial information. Let's concentrate on the initial pH. Initially, I haven't added any sodium hydroxide. I can just totally ignore that. Initially, all I have is 100 milliliters of 0.5 molar HCl. And we say, oh, HCl, we already know that's a strong acid. That makes life so simple. We know for a strong acid like HCl, however much that we start with, that's how much H3O plus we made. So in this case, we started with 0.5 molar HCl, which means we're going to generate 0.5 molar H3O plus, because that's what strong acids do. They completely dissociate. So my pH is going to be super simple. pH is just negative log of H3O plus, so it's going to be negative log of 0.500, which means my pH is going to be 0.52, oh, nope. Sorry, looking at my wrong thing. 0.301. Done. That's all I need to do. So initially, I don't even worry about the sodium hydroxide. All I look at is that strong acid. Now let's look at after I've actually added some sodium hydroxide. So now I do have to keep this guy in mind. And I've put my equation down there just so we can keep it in mind. So since we're adding something at this point, we're going to use our table that we use when we add things, which is our BARF table. Beginning moles, added moles, reaction, final moles. That's what we're looking at. So we say, okay, initially at the beginning what I had was the H3O plus. So I can't plug in the molarity. I have to use this to figure out the moles. So 100 milliliters is 0.1, oops, I'm going to read that, 0.1 liters. And I just do 0.1 liters times my 0.5 molar, because that stands for moles per liter, and that will give me the moles, which is 0.0500. Same thing for the hydroxide. Now I'm adding 50 milliliters of it, which is 0.050 liters, and it is 0.2 molar. So I multiply those, and it means that I'm going to add 0.0100 moles of the hydroxide. I really don't worry about my waters. Just like in an ice table, liquids and solids don't really care, so I'm just going to ignore that guy. So now I do what I always do in a BARF table after I figured out what I began with and what I added. I pick the smaller number, which in this case is 0.0100. I'm going to subtract that from both of these. So that will use up all of the hydroxide and leave me with 0.0400 here. So this fits in with our expectations. We had that pH curve. So that should say pH. Ooh, that's really bad. pH. And we had this general curve that looked like this. And we were before the equivalence point here. We were down here, and we said it should be pretty acidic. So we should have some acid left. And we look, what do we have left? Acid, and we have 0 base left. So now, since I have H3O plus left, my pH is really easy. I know pH is negative log of H3O plus. So I'm just going to plug that in, but I need to be careful because this isn't the concentration of H3O plus, it is the moles. So I can plug that in as the moles, but a concentration is moles over liters. So I need to plug in here the total volume I have now so I can get this new concentration. So if I look back, I started with 100 milliliters and I added 50. So 100 milliliters plus 50 milliliters tells me that I have 150 milliliters total. Or when I plug it in here, 0.150 liters. So when I plug this back in, I need to keep in mind that these brackets mean concentration. So I just put an extra step in here. I do plug in this guy from the table, but I just put it over the total volume that we have here and get that ratio. So if I do that and do the math on that, I find that my pH is 0.574. And that makes sense because we knew this was before the equivalence point. It should still be very acidic. Beautiful. Now, every time we do a titration problem, it's going to look like this. Let's look at the next one. Now we want the pH after we added 300 milliliters of sodium hydroxide. So we say, okay, I'm adding the sodium hydroxide, which means I need to do my BARF table. I'm going to do the same thing. I'm going to cross out the water and plug in my moles. The beginning moles never changes. I still have 0.1 liters. Oops. Let's just go back. I still have 0.1 liters, and it's still 0.5 molar. So I'm still going to have 0.05 moles of H3O plus to start with. Now the base I'm adding does change. So that depends on how much I'm adding in this particular step. So now I'm adding 0.3 liters, right, 300 milliliters, and it's 0.2 molar. So now I'm going to add 0.06 moles of my base. So now I do the same thing. I look and see which one is smaller. In this case, this guy is smaller. So that's what I'm going to react. That's my limiting reagent. I can't react any more than that. I realize I'm getting a little off key here, but there we go. So I had 0.05 under the H3O plus and 0.06 under the OH minus. So once I subtract, I have none of the H3O plus left, but I have 0.0100 moles of the OH minus left. And again, we can think about if that makes sense. So we had our pH curve, and we knew our equivalence point was at 250 milliliters. So 300 would be about right here. I should be past the equivalence point, which means I should have base left. And if I look, yep, that's exactly what happened. I used up all of my acid, and what I have left is some base. So we say, all right, no problem. I have some strong base. I definitely know how to get the pH of that. I'm going to start by getting the POH, which we know is the negative log of the OH minus concentration. So same thing as we just had dealt with. We do have the moles of OH minus that we can put on top, but we need to make sure we put that over the total liters because these brackets stand for a concentration. So we go back. I started with 100 milliliters. I added 300 milliliters. So I have 400 milliliters total, which means I'm going to plug in 0.4 liters down here. Just turn that into liters. And if I plug that guy into my calculator, I get a POH of 1.602. Now that's a POH. Really simple though. A pH is just 14 minus whatever my POH is. So 14 minus that gives me a pH of 12.398. And once again, we say, oh, that makes sense. On my pH curve, I was past the equivalence point. I was up at this really high part, so my pH should be very high now. All of my strong titration problems are going to look similar to this. Like I said, I recommend the first thing you do is just figure out what type of titration you have. Then make a little sketch so you know what to expect at each point. If we figure out the volume needed to reach the equivalence point, then for every other step we can figure out where we should be on the curve and if our answers make sense. Once you're trying to figure out the pH after adding a certain amount of acid or base, same basic procedure every time. You write a reaction, you make a BARF table out of it, you see what you have left at the end, and you get the pH from there.